This is lecture number 5 on anthropogenic climate change. I decided to reorder a little bit the lectures because I don't know exactly how much time we have left until the end of the semester. So I wanted really that everybody gets some exposure to global warming, climate change, and therefore bring this topic first now. There are two main sources of information. The book, of course, would be chapter 13 on climate change. But there's also the Intergovernmental Panel on Climate Change's assessment report. It would be the 5th assessment report, the very recent. And there's a document, Summary for Policymakers, SPM, which I've posted on the class webpage, which contains a really nice, succinct summary of all the findings of this report. So here's some sources of information. In the center, you see the book cover of the IPCC assessment report number 5, appeared 2013. So that's a while ago. And right now there's the 6th assessment report is underway, but it's not finished yet. So we therefore have only this 5th report. It's a little outdated almost now, 7-8 years ago. But that's all what we have. There's a follow-up report 2018 from the IPCC here shown on the right side. And this is a special report on the consequences and impacts of global warming if the global warming would amount only to 1.5 Celsius, which we, of course, know is probably going to be not true. We are in some countries today, nowadays, we already have exceeded 1.5 Kelvin or Celsius warming. There are some national assessment reports here, for example, climate change and evidences and causes, national climate assessment from 2014, so climate assessments for the United States, and there's also a report. So we are going to cover in this lecture 3 key questions on climate change. First of all, is global warming real? Second, what has it to do with human activity? And how will climate change evolve into the future? So these are 3 questions. Accordingly, divided this lecture up in 3 parts. And in this specific slide series, we cover part 1 and part 2. So let me start with a few citations from those assessment reports and how they changed their language over time. In 2001, one of the early reports, they simply talked about that there is, from the observations, there's some evidence giving a collective picture of a warming world. So that must be essentially 20 years ago. Okay, so it was sort of a modest language. 6 years later, in 2007, it sounded a little bit differently. They said warming of the climate system is unequivocal, as there is now evidence from observations and so on and so on. Okay, so unequivocal meaning there is no doubt and misunderstanding. So this was 2007. So latest report 2013 now not says only that warming is unequivocal, but it's also unprecedented, those changes which occurred over decades to millennia. Okay, so the language gets stronger and stronger as there is more and more evidence that climate change is real and is threatening our societies. So let's start with part 1 of this series. Here, what are the observed changes, of course, to the physical climate system? So here you see a simple summary of some of the changes which have occurred as a consequence of climate change. And the important message is that all those changes are simply consistent with warming. So we have warming of surface temperatures, of sea surface temperatures, of temperatures in the ocean in terms of the ocean heat content. We have air temperature or tropospheric temperature is measured by satellite observations are warming. Of course, then the snow cover is decreasing, glaciers are decreasing, sea level is rising because of the thermal expansion of the seawater. Sea ice is declining, water vapor is increasing, so specific humidity. So, and this is just like a small subset of changes, but the important message here is that these changes are all consistent with each other. So if you look at individual changes, let's say sea level rise, okay, so there may be this and there may be some doubt on how well we can observe those changes and are they really significant, but it is also important that there are multiple sources of evidence or multiple changes which we see in the climate system, which all together give a consistent picture of global warming. So it's maybe not enough just to look at one quantity or one variable. It's like so here, these are some graphics taken out of the 5th assessment report. Okay, it's also abbreviated IPCC AR5. AR meaning assessment report in the 5th of 2013. Okay, so of course we have all seen this. It's just a temperature record over land and ocean, so surface temperature record from pre-industrial to almost today, and of course it's a steady increase. Interesting, there are various curves on top of each other plotted, so these are from different groups who take and collect those data and those information and put together a global record of temperatures, and they mostly agree with each other. You cannot even distinguish them from each other. There's high confidence that this is really an exact representation of what happened really over these years, so that global warming temperatures are really increasing. How much is the increase? Now, if you think from pre-industrial, I mean, this is relative to some climate normal, which is probably here in between maybe 1960 to 1990 or something. Okay, so they started at minus 0.4. These are anomalies with respect to that climate normal, right? Minus 0.4. Now we are maybe at 0.6, so it's at least 1 Kelvin warming, which we went through. I would almost argue it's already exceeding 1 Kelvin warming because we don't really show here in this specific graphic the latest measurements. So at least 1 Kelvin warming we have been going through since pre-industrial times. And then here some of more subtle time series over the same period, actually starting in 1900. So, for example, changes in spring snow cover. It is, of course, something which is much more difficult to measure. They're probably not as good and as many observations as for temperature. But nevertheless, I think even with my eye, I can see there is a decline in snow cover, as you would just simply expect from an increase in temperatures. Much more clear, however, is the decline in Arctic sea ice extent. Arctic sea ice extent has been going down dramatically. This is the summer Arctic sea ice extent, so probably September, during a time when the Arctic sea ice is at its smallest extent. So just look for comparison. We started out at 10 million square meters or whatever that was, and now we are down at, let's say, 6 or even 5. So this is like halving over the past 100 years, the amount of Arctic sea ice extent. So this is very dramatic changes here over the Arctic happening in terms of sea ice. Ocean heat content is going up, likewise, like the temperatures are going up. So what is ocean heat content? Essentially, it's the column integrated down to deeper parts of the ocean, not just at the ocean surface. Column integrated amount of heat in the ocean. Essentially, it's temperature over the deeper parts of the ocean, including the surface ocean. Okay, and so, I mean, that's what you would expect, that this goes up. It's measured in joules, so it's energy. Different groups, different approaches, all lead more or less to the same results. It's also interesting, these curves converge. Here, during the early periods of the record, there was more uncertainty than there is nowadays, as we have more and better measurements. The sea level, height of the sea level is increasing over time, again, because of the thermal expansion of the sea water, warmer water occupying more space. Therefore, sea level is changing. Of course, to a smaller extent, sea level rise is also due to the melt of land ice in forms of snow, and probably mostly ice caps. So it has nothing to do, the sea level change has nothing to do with the melt of sea ice, because sea ice is already displacing water and therefore is not, as it melts, not changing the sea level. Here are some panels taken from the more recent National Climate Assessment Report, appeared in 2017, so it covers a little bit more years than the IPCC report, the fifth one. But essentially the same picture: land surface air temperature, sea surface temperature, and sea level data are all going upward as expected. In each of those cases, there are measurements from different groups, and they agree more and more and better with each other as we go to the more recent time periods, and there's more disagreement in the early periods. Okay, so this type of information can be seen in that. More of this from the more recent report. Tropospheric temperature. With tropospheric temperature, they mean satellite derived and maybe also radiosonde observed temperatures of the troposphere itself. So it's not at the surface, but within the troposphere. So in upper air, one could say. Okay, ocean heat content, we have already seen this, 5 data sets. Specific humidity, clearly an upward trend, as one would expect, as the sort of as expected from the Clausius-Clapeyron equation, that a warmer air or warmer temperatures, then there will be more humidity in a specific sense, so in absolute sense, not relative humidity. Snow cover declining. Arctic sea ice, now you see here 2 numbers. This would be the September Arctic sea ice. This is very dramatic if you think about it. It started at 3 and now we are down to, let's say, 1.5. So it's a decline by 50% over those past 20 years only. So very dramatic changes in Arctic sea ice. And the annual amount of Arctic sea ice decline is a little less pronounced, simply because in winter is during polar night, is always cold enough to refreeze the Arctic Ocean, no matter how much the warming will be in summer. The only difference will be that the refreezing Arctic sea ice will be much thinner, but this is not being measured here in this slide. It's just the extent, so the amount of Arctic Ocean which is covered with sea ice, whether it's thin or thick, it doesn't matter. And here glacier cumulative mass bands. Okay, glacier ice is of course going down as expected. Another version of land and ocean temperatures. So this now includes some of the very recent increases, strong increases in temperatures. Interesting is also if you look at this in a decadally average sense here in the lower plot, essentially you see that since basically World War II, every decade was warmer than the decade before. This is quite amazing. So why decadal averaging? Well, because we know that there's a lot of noise in the data. Even if you take global mean, annual mean temperatures, there may be events which are related to natural variability, like from ENSO or other events, which can, for natural reason, change the temperature from year to year a little bit. And so we call this now noise or internal or natural variability. And only if you average over long enough time periods, you essentially decrease these influences And what you end up with is seeing these long-term trends, which are very likely due to anthropogenic activity. Here we see a comparison of historical simulations from many climate models, the so-called CMIP5 climate models. CMIP5 meaning coupled model intercomparison project 5, so the fifth coupled model intercomparison project. So this is a bunch of models from global modeling groups who participated and submitted their simulations for the write-up of the fifth assessment report. And the outcome of the individual models is shown here by that uncertainty. It's probably plus minus 2 sigma or something like that, or plus minus 1 and 2 sigma, or the min and max and sigma, whatever. But the mean is actually more interesting. It's this orange curve here in the background. And it's really nice to see how well in the mean, the ensemble mean of all those models, and these are at least 20, maybe even 30 models who participated and contributed, which are included in this report. And their temperature is matching very well the actually observed temperature shown either in green or whatever color it is, red and black. So these are the observed temperatures or reconstructed temperatures since pre-industrial times. And I mean, it's just sort of a test or kind of showing that the models are doing a good job in reproducing the history of past temperature. So it's sort of a sanity check for those models, whether they are any good. Okay, and I would say that they are doing actually a very good job. So here, this is a somewhat different view. Now you see a spatial map of the changes in surface temperature over the past 110 years or so. And so it allows you to see where temperature changes have been strongest. And so the darker the color, the stronger are the surface temperature changes, like going up to 2.5 degrees Celsius. It's quite amazing. And it's strongest, these temperature changes, over land. So the Asian, European Arctic, the North American Arctic, and I mean here you see also quite some changes down here, which is not belonging to the Arctic, of course, South America. But in general, I mean, if they would show data here over the northern part of the Arctic, which is mostly ocean, the changes would be even stronger. Okay, so there's warming almost everywhere in terms of surface air temperature, mostly over land, mostly over the higher latitudes, and mostly, of course, over the northern hemisphere, because this is where most of the land is. And so of interest is also this area is to the south of Greenland. This is the only region where we see actually not a warming of temperatures, which is, to my understanding, related to the slowdown of the Atlantic meridional overturning circulation, which is sort of that conveyor belt of surface ocean water, which brings warm water from tropical, subtropical areas towards the north, or North Atlantic drift, it's also sometimes called, or it's also part of the Gulf Stream system, of course. Okay, so there's an apparent slowdown of that northward transport of warm air from the tropics to the high latitudes, resulting here in a gradual cooling to the south. Precipitation changes, if you look at this figure here on the top right, to the extent that it is even possible to reconstruct those precipitation time series over this long period of time, but can see there's not much of a trend. in the global mean. Does that mean that precipitation is not changing? No, of course not, because if you look at maps of global changes in precipitation, you see that there are, let's say here from 1951 to 2010, we see that areas of increases in precipitation, shown in blue, but not everywhere precipitation is increasing, it's also decreasing, particularly pronounced here in the Mediterranean countries. So if you look at the global mean as done here in this time series, then there is not much change in precipitation, simply because some areas get more and other areas get less precipitation over time. Also, you see here there are two plots. One is for the long period, 110 years. Of course, they are not as good data over this long time period, and the changes seem to be also weaker. But here, if we go over the shorter period from 1950 to 2010, we see that those changes in precipitation are getting much more pronounced. There are many other climate quantities which are also changing as a consequence of global warming. And here I'm picking and showing one particular interesting quantity, which is the amount of tropical storms or hurricanes occurring over time. And so that this big interest, and there's been the question of whether hurricanes are getting stronger or more frequent, and which type of hurricanes are getting more frequent. And there's been, in particular in the 2000s, a couple of studies because apparently there was this increase in hurricanes, like Katrina happened during that period, and everybody thought that, okay, oh God, global warming is causing more hurricanes and stronger hurricanes. And so here I show you over the past 55 years, the number in each years of the particular types of hurricanes occurring worldwide. And if you look at those pinkish, or like on the top of those columns, you see there's sort of maybe a little bit of upward trend. Actually, yeah, it looks like an upward trend, but then there's also again a downward trend. But if you just focus, for example, on the most strongest category 3, 4, and 5 hurricanes, then of course there's much less data available, and so there's this up and down. And so it's not very clear whether there is now a trend in the number or intensity of hurricanes or not. There's been a study by Knudsen et al. Nature Geoscience 2010, where he concludes that it remains uncertain whether past changes have exceeded the variability expected from natural causes. So essentially, there's not conclusive evidence that the number or strength of hurricanes and tropical storms in general have been changing over time. But as far as I know, it is expected that the number of the particularly strong hurricanes, category 5, should increase over time. At least this is what actually the study by Knudsen et al. Suggests. And the study is based on model simulations. And also from a physical understanding, it would make sense because as sea surface temperatures and ocean heat content gets warmer, there will be more moisture available in the atmosphere. And of course, the condensation of that moisture in terms of latent heat release is what is driving those hurricanes. So from that perspective, it would make sense that the number of the particularly strong hurricanes or tropical storms should increase over time with global warming. So now to the second part of this lecture. What are the causes for those changes which we have seen in the first part, and which hopefully convinced you that climate change is a real phenomenon, it's significant, and it's not normal, it's just not part of the normal natural variability. Okay, so what are those causes? Are humans to blame for climate change, for example? Okay, and so again, I can only show this and explain this here in those slides in a very abbreviated form. You should definitely read along in the book. I would suggest that for now you read in the book the first 10 sections of chapter 13 on anthropogenic climate change. So sections 13.1 to 13.10. It's relatively easy to read, shouldn't take you too much time. And it gives you some good understanding of climate change, of its causes, of course. Okay. Everybody knows that the main culprit for anthropogenic climate change is that more or less steady increase in anthropogenically produced carbon dioxide. Here you see in this slide the so-called Keeling curve, which is the red ups and downs, which show you the seasonal, there's a certain seasonal cycle to the carbon dioxide. That seasonal cycle has something to do with the seasonal growth and decline of vegetation over the northern hemisphere. So during summer, the vegetation is actually taking in some of the surplus of atmospheric carbon dioxide from the atmosphere and building it into plant mass, leaves and so on, and that drives on average down the carbon dioxide in the atmosphere. But then in the next winter, of course, the leaves fall from the tree and decay and release most of that earlier captured carbon dioxide again, unless it is captured in terms of wood. Okay, but I mean, this is a topic from by itself, even this interesting seasonal cycle. But the black curve here shows you just this steady increase, sometimes more strong, sometimes less strong, of carbon dioxide concentrations. If I remember this correctly, nowadays, I mean, this is already an outdated curve, of course, it ends more or less at 2012. Nowadays, we are at 410, 415 parts per million atmospheric CO2 concentration. Yeah, interesting, this black curve shows here CO2 at the South Pole, where that seasonality in the seasonal cycle is much less pronounced. So this also has something to do with that it takes some time to mix the northern hemispheric air with the southern hemispheric air. And essentially, you're eliminating, if you just look at the South Pole, you're eliminating the effect of this seasonal growth and decay of vegetation over the South Pole. Okay, anyhow. And this Mauna Loa curve is a Hawaiian volcano. And this is where I think Ralph Keeling or whatever his name, Keeling curve, it's called. This curve, so it's named after that person or scientist who first started to measure, take regular, weekly probably, atmospheric CO2 measurements on this site on Mauna Loa, which is a relatively remote site, so not much industrial influences on this site. Okay, so not only CO2 in the atmosphere is increasing, it's also increasing in the ocean. So this is the dissolved carbon dioxide. Different measurements, they're all pointing upward over time. Of course, the record is relatively short, only maybe 20 years short since people or scientists started to measure it. And at the same time, shows you the pH content or the level of acidity of ocean water. If pH is going down, clearly it points down towards lower pH levels. That meaning that the acidity of the ocean water is increasing, which has, it's called ocean acidification, and that problem it's bad news for many organisms who live, calcifying organisms like shells, or I mean even very little zooplankton animals which live in the ocean and have a harder time to build those shells because the acidification of the ocean. And then of course the problem goes up into the affects the entire ocean food chain, because the very smallest animals are being then being eaten by larger animals and so on. Okay, so that would be ocean acidification. So where does all this carbon dioxide go, which we, by burning fossil fuels, emit into the atmosphere? The good news is that only less than half of it stays actually in the atmosphere and leads to the buildup of carbon dioxide in the atmosphere. And 30% is taken up by the ocean, so the carbon dioxide is dissolving into the ocean and therefore also increasing the carbon dioxide content in the ocean. But also terrestrial ecosystem are taking up some, actually it's quite some portion of the carbon dioxide, 30% of it. Probably one can think of that this leads to more growth of vegetation, for example, in terms of trees and so on. So the cycling of carbon, not just carbon dioxide, but the different forms of carbon in the Earth global system, that's called the global carbon cycle, and that's like something on its own you have to study and you have to understand. If you're interested, you can look at the IPCC report in chapter 6. They talk a lot about it, and essentially the highlights of this carbon cycle are shown here in this diagram. Here I really like this study. This is appeared in Journal of Climate, relatively old study, 2004, by an NCAR scientist, Jerry Meal. But it shows you, or it can be thought as an attempt to attribute what is climate change due to. So it's called climate change attribution. And so what they did in this study, they ran this particular climate model from DOE many times from pre-industrial to today or so. But in one simulation, here shown in sort of brownish goldish colors, they used all the known forcings to drive that model. Okay, and then when you did this, and all the known forcings are shown here, actually, not just the greenhouse gases, not just carbon dioxide, also changes in solar activity, changes in ozone, changes in volcanic activity, changes in sulfate aerosols. So if you put all that information, that known history of forcings into that model, the model reproduces quite well the observed history of temperatures shown here in black. So indicating the model is not only doing a good job, it's also considering the right amount and the right strength of the individual forcings. And what they then did is they repeated these model runs, but then now in these colored time series, they were only just using one forcing at a time and keeping all the other forcings, either natural or anthropogenic forcings, keeping them at their pre-industrial unperturbed condition. And so, for example, the blue curve, the blue curve shows you the changes in temperature that model predicts if only carbon dioxide and methane and these greenhouse gases are increasing according to the observed history, and all the other changes kept constant. So you see these strong increases in temperatures over time. Here, within 90 years, temperatures changed or increased by 0.7 degrees just due to the effect of the greenhouse gases. Whereas if you just changed the amount of sulfate aerosols in the atmosphere and kept everything else constant, then the model predicted a cooling of maybe minus 0.3 Kelvin over that period of time. And so sulfate aerosols are another important forcing factor, but they actually lead to cooling. And ozone, tropospheric ozone in particular, is also a greenhouse, very potent greenhouse gas. Remember from previous lectures, we talked about how ozone, the absorption band of ozone is just in the middle of the terrestrial window, and it's very effective greenhouse gas, therefore ozone. And so anthropogenic forcing factors would be the greenhouse gases, would be ozone, and the sulfate aerosols. And this is all very nicely explained in Hartmann's book. And they also changed natural forcings. Natural forcings would, for example, be changes in the strength in the output of the sun, in association with the 11-year solar cycle. And there have been small increases over time in the strength of the sun. Actually, in more recent years, during 2010, and since 2010, the output of the sun has been actually decreasing by quite a bit again. But I mean, these are natural changes, and if you take this into account or just the solar output, you get a small warming, but changes in solar activity themselves cannot explain the actually observed warming. And similarly, volcanic activity, which of course leads to a cooling, that's probably the Pinatubo eruption here, and that's, I guess, El Chichon or something. What was the name? Whatever. Okay, so each of those volcanic eruptions has a relatively strong, long-lasting effect, a cooling effect on global temperatures. Anyhow, so the essence of this slide is that only if you include the anthropogenic forcing factors, which would be aerosol, changes in ozone, and greenhouse gases, only then you can replicate past observed temperature changes with that model. And so this can be considered as one way of attributing climate change to anthropogenic reasons. So this slide is somewhat similar to what I've shown before. And now these are results from those CMIP5 models, which are models which have been run maybe in 2010 or so. So they are not the latest version of models, but they're much more modern and better than the model from the previous study, which was done in the 1990s or 2000, so 10 years younger. Anyhow, and these are also multi-model. It's also a multi-model study. So again, it shows you, I mean, that slide we have already seen before. It shows you again that if you take the ensemble mean of all those models and put in all those models, the observed and known history of forcings, then these models replicate very nicely the observed changes in temperatures over the past 150 years. And so the interesting slide is now here, panel is here on the right side. It shows you the temperature changes predicted by the same models, these CMIP5 models, but in this case, these models see only the natural forcings, so volcanic activity and changes in solar output over time. And if you do this, these models in the ensemble mean, they essentially predict a flat curve. Now, it's not changing much the temperatures over time, and the observed changes in temperature here are going, of course, positive, and they are outside the uncertainty range of those individual models. So again, proving that only by including anthropogenic changes in forcings in terms of greenhouse gases and other forcing agents, only then the models can replicate the observed temperature changes. And if you don't do this, if you only use natural forcings, then the models cannot reproduce those temperatures. These are much simplified versions of more or less the same thing. Only showing you here are decadal averages, so not year-to-year numbers of land surface temperatures, land and ocean surface temperatures. In black in each of those panels, you see the observed changes. In bluish colors, you see if the models are run only with using natural forcings over time. Again, this is sort of not much of a change, flat line temperature, land surface, global temperatures, and global heat content, ocean heat content. And again, only if you include information about anthropogenic forcings, the models are replicating. This is a somewhat more complicated slide here, but it summarizes essentially the first 10 chapters of Hartmann, where he goes into quite some detail on the role of individual forcing agents in contributing to global warming. And you see here different forcing agents, starting with CO2, going down to things like aerosols, land effect from land use changes, and changes in solar output. And zero would be here along this line. And interesting is the bar, colored bar, shows you the strength of the forcing. It's the so-called radiative forcing measured at the top of the atmosphere. So by bringing in carbon dioxide, by how much did the energy balance at the top of the atmosphere change? What are the expected changes? And just by bringing in carbon dioxide in the amount, let's see for what year are those, it's probably 2010 or so. So since 1750 to 2010, carbon dioxide alone led to a forcing of around you see the numbers given here, 1.6 or 1.7 watts per square meter. There's some uncertainty associated with it, but the uncertainty range is relatively small compared to the overall length of the bar. So therefore, there is a very high confidence that this result is true. So the level of confidence is very high. And you see now the contribution of other greenhouse gases and forcing agents. The greenhouse gases, we have relatively high level of confidence, either it's VH, very high or high. Here you see some mediums. So these are other gases emitted by industrial activity, probably into the atmosphere, and what they cause. And actually CO, for example, there are some byproducts being produced. CO when it's being emitted, it produces CO2 and methane and ozone and whatever. Okay, a little complicated stuff. But of larger interest are the effects of aerosols, which I hinted on before. Aerosols have very long error bars associated with them. There's the so-called direct aerosol effect and indirect aerosol effect. Indirect aerosol meaning that bringing aerosols into the atmosphere changes the optical properties of clouds. Maybe clouds get brighter because there will be more cloud droplets. Clouds may also become more long-lived. But there's very large uncertainty on those effects, and the uncertainty is almost as large as the effect, the best estimate for that effect. But it is estimated that the direct effects, or the direct radiative effect of aerosols is overall negative, and also the indirect effect is negative. But there's large uncertainty, in particular here you see the L, in particular with respect to the indirect aerosol effect. Some aerosols can actually warm, as here shown in the gray bar, which is the aerosol. It's the black carbon effect. So if you burn biomass into the atmosphere, sometimes the burning is not complete and leaves, you get like this black stuff in the atmosphere, so-called black carbon. So it's not fully burned biomass material, incomplete burning. And if that settles then down, for example, it may make snow darker. and then therefore decrease the albedo of snow. This is of course a positive forcing. It may also change the color or the reflectance or the albedo of the atmosphere itself, because these particles are dark, and again, dark substances in the atmosphere would reduce the albedo of the atmosphere and therefore warm the atmosphere. So therefore black carbon has a positive forcing. Other types of aerosols have a negative forcing because they mostly lead to an increase of the albedo of the atmosphere, reflectance. Okay, so if you think of how strong these forcings are, they're all anthropogenic. Here you see anthropogenic, and there are some natural ones. Actually, volcanic one cannot show because it's episodic. It doesn't make sense. To give a number. Of course, right after the volcanic effect eruption, you have strong forcing effect, but that goes away over time again. But the really often discussed effect is from the sun, and it's estimated to be very, very small. So this is important to know, because many climate change skeptics often use the sun as the reason of why temperatures have been changing and are changing. But the sun, if you look in detail, the actual changes in sun output cannot explain anything. So the total anthropogenic forcing, taking all these anthropogenic forcing factors together, the total forcing amounts to, in 2011, it amounts to 2.3 watts per square meter. And the level of uncertainty, the level of certainty, one should say, a level of confidence, is very high that these numbers are correct. So the biggest uncertainty again come from those aerosols. But I mean, these bars are so strong, and if you add them up, you come up with very large numbers. Okay, and so there's no doubt that human activity on Earth since pre-industrial times has led to a positive forcing of the climate system in the amount of 2.3 watts per square meter. So this is now the end of this lecture, part 1 and part 2. This is of course a very brief summary of anthropogenic climate change. Please read the first 10 sections of chapter 13 in the book, where Hartmann describes the role and the amount, and it gives interesting information on these individual forcing agents. Okay, so this is, I think, the end of this part 1 and part 2 of this lecture on anthropogenic climate change.